Swayam Prabha. Digital India. Educated India.
Hello everyone. Now today's topic is practical statistics. In the last session we have discussed the sampling techniques, that is sampling techniques for textile materials. How do we collect fiber, yarn and fabric samples for testing with approximately unbiased manner, and then after testing our main idea is to analyze the data. So in this session we will try to understand the analysis technique through the application of some basic statistics which is used in textile industry. So if you see the data, when we obtain the test data, we get the particular distribution. There are different types of distributions available. So, but in textile material, its variability is very high. So here we assume that the variation takes place in random fashion without any biasness. That's our basic assumption. So the distribution is assumed to be in normal distribution. So here in this table the strength value is obtained. So there are different test samples. After obtaining the strength value, we can classify the or group the values at different levels. Like in this table, the strength value is actually ranging from 110 to 170. So for a particular material, textile material, the strength value is ranging from 110 to 170. Unit may be anything. So first we have to classify these values in different groups. So what we are trying here, we are in this range is the 60. So 170 minus 10. So within this 60 range, so we are dividing it to 5 range of 5. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Such 12 classes we will get. So if you see here, at lower strength value, the number of readings are 2. So 110 to 115, the number of readings are 2, 116 to 120, again 2. So at different range, different classes, we have got different number of readings, number of test values, strength values here. After that, we can plot this data in a particular form, in histogram form, and where in the x axis we get the strength, here the class value, here it is a strength value in x axis, and in y axis it is a frequency, number of times it occurs. And when we plot this, we get this type of curve where at the center the frequency is maximum, and this bell shaped curve is distributed evenly in both the sides of this central point. So in normal distribution, the central point is actually here mean, mode and median, they coincide. If this mean, median and mode coincides at the central point and the distributions are even in both the sides, then we will call it as normal distribution. So more or less in textile material, although variability is relatively high, but we can consider the distribution as normal distribution. So for our all further discussion, we will actually assume the distribution as normal distribution. And if we see the central point represented by mu, which is nothing but mean, median and mode. What is mean? So if we take all individual data, like between 110 and 115, the two readings are there. So let us see 111, first is 111, second is 114. So these two data are ranging within 110 to 115, and between 116 to 120 we have two data like 117 and 119. and 119. So this is the first class, second class. In third, between 121 to 125, we have 5 data. So say 121, 122, 122, 123, 4, 125. These 5 data are in class 3, class number 1, class number 2 and class number 3. Between 126 to 130 we have 12 data. So what we are doing, we are arranging this data in ascending order up to say 166 to 170. So within this last class, that is the maximum value of strength, only one data is there. So we can say it's a 168. This is the last data. So when we are adding individual data and then multiply by the total number of data point, we get mean value. And what is mode? Mode, we know that the frequency of the data where frequency is maximum, that will be called as mode. And median is the, when we arrange in ascending order entire data, the data point at the center, it's called mode, the median. So theoretically all these 3 value is coinciding at a point which is mu. It's represented by mu, which is mean, median or mode. Now using the standard deviation formula, we can calculate the standard deviation of all individual data. We can calculate the standard deviation, and which is represented by sigma. Now the nature, basic nature of a normal distribution is that central value, here it's a mean, and plus 1 sigma in the right side, higher side, and minus 1 sigma in the lower side, which will actually consist of typically approximately 68% of data. Here we have certain data. Now let us assume the total number of data point are 100. Total number of data point here is given 100. Total readings we have taken 100. And here say mean, typically it will be around say 140, say 4. 144 is the mean value, which is mu, and 100 is the total number of data point is denoted as n. And if we calculate the standard deviation using the standard formula. Suppose standard deviation we have got say 5, okay, and so 5 or 10, suppose we get standard deviation 10. So from this relationship what we get, that the total number of data point here 100, so mean 144 plus 10, say 155. So let us, for our discussion, let us assume this is not 10, let it be say 5. Let it be 5. So 144 plus 5. So this zone 144 plus 5, 149, and 144 minus 5, it's 139. So this value is 149 and this is 139. So between 139 and 149, in this range 68% data are lying. That is, out of 100, 68 data will be there within this zone. I am not discussing about this or as per the table, but typically it is 68%. And similarly, if we go beyond that, plus minus 2 sigma, that means 144 plus 10, 144 minus 2 into 5, 10 equal to 134. So between 154 and 134, in this zone typically there will be 95% of data are lying within that zone. That means total out of 100, 95 data will be there out of 100. If we consider this is 100 data, so that between 134, so that is between 134 and 154, so 95 data will be there. I am not referring to this table because I have assumed it's 100 number of samples. So similarly, plus minus 3 sigma level we will get certain data approximately 100. So 95% data are within plus minus 2 sigma limit. So 95% data are within 2 sigma limit out of say 100 data. That means 5 data point will be beyond that. So approximately 95%, the 5 data point will be beyond this limit. In this zone 5 data point will be there, in this zone, now in this zone, and in the total 5 data point. So here there will be 2.5 data, here there will be 2.5% data. That means 100, we have taken 100 readings. So what does it mean? So beyond 2 sigma limit, 2.5% means 1 in every 40 readings will be more than that plus 2 sigma limit, and 1 in 40 will be less than 2 sigma limit. So this is the basic understanding of the normal distribution and basic properties. So this property we can assume for our normal calculation. So what we have already discussed, it's a symmetrical about the central value. So central value is the arithmetic mean, median and mode, that I have already discussed in detail. So already it has been discussed, approximately 68% data are falling within plus minus 1 sigma limit. That means typically 34% data are more than the central value, and at plus minus 2 sigma limit approximately 95% of data, that is 5% data are falling out of that range, which means that 1 in 40 data are greater than the mu plus 2 sigma. Similarly, 1 in 40 are less than mu plus 2 sigma. Now, the problem which we have discussed, so this normal distribution, it deals with the population value. Suppose in our example, earlier example, we have taken say 100. Now the population, say it's a 10,000. 10,000 readings are there, and theoretically, suppose we have calculated the individual data and we have plotted the values, so individual data, so that we have plotted individual values for all 10,000 data, and we have got this type of distribution. So these are the individual data. Now the problem here, we know that we cannot test individual data, that's a theoretical concept. We cannot take the individual data. So here what we have to do, as we have already discussed, we have to take the sample to reduce the cost, reduce the time required for testing. So but in our case, the whole population is available for testing. Due to our time constraint, we don't do that. So sample we collect, as we have already discussed. So whole population is not possible. For that, what we do, we assess the sample distribution. we can only do the whole population where number of sample is less. Suppose I have got 10 apples and I want to know the weight, average mass of the apples. What I can do, 10 is very small number, and then I can take the mass of individual apple and I can get the mean or standard deviation. But if I have say 10,000 apples and if I want to know the mean and standard deviation of the mass, then the problem would be there. For that we need to take the sample, and here onward we will discuss how to use the sampling concept and analyze the data. One thing we should be clear, that if we ideally we should, if we take the individual, all individual 10,000 mass value and get the average and mean and standard deviation, that's the ideal case. But that's not possible. We take small quantity of material. In this case, say we can take say 20 apples and take the mass, which is called sample mean, and that mean we cannot tell that that mean is exactly equal to the population mean, but we will get some idea about the mean value and how to treat this deviation, that we will discuss analytically. So, by sample analysis we can achieve two main objectives. First objective is that when we wish to confirm or reject that a change in anywhere had happened has got real effect on the property. In statistical term, we call it as significance testing. Whether there is a significant change or not, that we analyze. And second objective is that to estimate some characteristics of the population, like we are estimating that, as we told that whole population mean is that x bar p and sample mean is that x bar s. This is the theoretical value based on, in earlier example, say 10,000 values weight of individual apple, and here based on 20 readings. Now whether this is representative of the entire population or not, that we cannot surely say, but through statistical analysis we can say how much it's correct or not, how much variation could be there or not, that we can estimate. So that's a estimation of some characteristics. Here we can say will measure that x1s, that is lower limit, and x2s sample. Through sample we can get one range. So this range, this limits, we can estimate the limits. So this limit, within this limit we can estimate that, okay, within that limit the population mean will definitely be there. That's called confidence limit, and that confidence can be of different level, say 95% level, 99% level. I will discuss. At different, typically there are, you can have 50% confidence limit, 60% also. Typically in statistics, in textile industry, we can consider 95% or 99% confidence limit. So this interval, this limit is called confidence interval. So now let us discuss the, what does it mean, sampling distribution. Suppose this is a population, as we have discussed, this is whole population where we have, say, 10,000 data points are there, and here what we are doing, we are, this is normal distribution. What we are doing, we are taking number of samples, each say containing 20 readings, 20 data point randomly. Now let us see, these are the individual, say 10,000 data point. Ten thousand data points are there. Now here what we are doing, we are taking 20 randomly, 20 samples. 20 samples if we are taking, and so if in each case 20 samples are there, and that means we will get 10,000 by 20, that means 500 such data point. So we take 20 readings, 20 specimen out of this population, and what we are doing, we are taking, and we are taking this sample 1, based on 20 readings, we are taking the mean. This mean we are putting, we are again plotting against that. This is the mean of 20, first, then second, third. In this way we keep on. This data point, each and every data point are average mean of 20 data point which is extracted from the population, and then if we plot, typically we will get another normal distribution. But here in each data point we have this, each mean value consists of 20 data points. This distribution, actually it's a sample mean, so this distribution is known as sample distribution. So their shapes are same, but the concept is that we take the sample of certain number n, here n is 20, and then we try to plot. And in sampling distribution we have seen this is x bar mean, here x bar plus 1 sigma plus 2 sigma, like this. Sampling distribution, that is you have individual data point, that is why we can calculate the standard deviation. But in sampling distribution we do not have individual data, we have mean of individual data, that is x bar 1, x bar 2, x bar 3, individual mean. So there we do not normally use the value that's term standard deviation. So the mean will be typically same because it's a overall mean. Mean of the sample means will be exactly equal to the population mean, because and this value here we should remember here that that's a difference between sample distribution and normal distribution. Here we use 1 into sigma, 2 into sigma. Instead of sigma standard deviation, in sampling distribution we use term standard of error. Standard of error. So SAM is equivalent to standard of error of mean. So this is equivalent. Okay, this standard deviation is used in normal distribution and standard error of mean is because we have taken mean. Here these are the mean value. We use term standard of error. Okay, and 1 or 1, 2, 3 are the level, 1 sigma, 2 sigma, 3 sigma levels in case of normal distribution. But here, and 1 sigma level means say 90, it's a 68%. 2 sigma level means 95%. Certain 3 sigma level means 99.99% typically. Here the level means at 95% level, as we have told in textile we use 2 proportion or 2 level, 95 and 99% level. In 95% level, instead of this 1, 2, 3, here we use a term called T. T is actually equivalent to 1, 2, 3 level. So T at 95% level, so this is T into SE 99. So at is T95, T99 like this. T at 95% level, T at 99% level. In this way it goes. So these are the basic difference between sampling distribution and normal distribution. So here it's written, take a large number of random samples. We have to always take random sample. How to take random sample we have already discussed. Each of n individuals, in our example it was 20 individuals were there. Plot the frequency distribution of mean. of each sample, which is also a normal distribution. That's we have taken the plot of means. Okay, and then this distribution is called sampling distribution. And as we are not going to take the individual data, total population, so we will not discuss in our calculation the normal distribution. Normal distribution is a concept. It's not possible practically to test all the data, that we know. So our idea is to take the sample and then do analytical analysis on that. So we will be concentrating only on sampling distribution because we are dealing with the samples. So standard deviation of sampling distribution of mean is standard error of mean. As I told, it's equivalent to this standard deviation in normal distribution. Here we call standard error of the mean. So in standard deviation, what we did, we have taken all individual data, 10,000, and we have calculated the standard deviation, okay, of population. Standard deviation of population. So we can call it as standard deviation of population. And what is standard error? It's a standard deviation of mean value, individual mean value in the sampling distribution. So standard, what is the individual data point, number of data points, say n. In earlier example it was 20. So which will be higher, standard deviation or standard of error? Numerically standard of error will be lower because the variability within these 20 readings, so 20 individuals are not considered. So there will be variability within each individual, say n number of samples, the variability is not considered. So this is only x1, xa1, x bar 2, like this. We are taking mean. So that's why we are eliminating that variability within the sample. So therefore the relationship will be standard deviation of population divided by under root n. N is the number of specimen, and we will discuss later, this is standard error of mean, and standard error of standard deviation also we can calculate. Standard deviation, so suppose we are taking the n reading and we are calculating the standard deviation of first value, standard deviation of second value, like this. Standard error of standard deviation, statistically it is expressed as standard deviation of population by under root 2n. Only this difference is there. In case of mean, it's under root n. In case of standard deviation of standard error of standard deviation, it will be under root 2n. That's the only difference. But statistically, one can go through the literature book. It's there. We are not going to discuss these derivations. So standard deviation standard formula is there. So standard deviation equal to under root summation x minus x bar. X is the individual data point value, like in our case it's a mass value. X bar is the mean and n is the number of reading, and degree of freedom is n minus 1, and standard error of standard deviation from this formula. This is the standard error of standard deviation. So in our calculation, our analytical approach, we will use standard error of mean, not the standard deviation. But the thing is that standard error of mean, if we want to calculate, we need standard deviation, and this standard deviation of population, it's not basically, you cannot calculate. Typically this is the, sometime it's a targeted value, or nominal value, or some specification is given. So these are the, and based on your daily experience, you can set the standard deviation. So this standard deviation cannot be calculated based on the large number of population. So because this standard deviation is a population standard deviation. Now so in number of sample in a particular, in number of readings in a particular sample. Now suppose, as we are discussing, 10,000 data points are there. So this 10,000 data point, depending on our on the level of this level of accuracy required, we can get the number of readings. How many readings in a sample should we take? Suppose 10,000, again I am taking the same example for easy understanding. Now what I am doing, if I take n equal to say 10,000, by some means I want to be very correct, I am taking all individual data, I am putting effort to take mass of all individual data. In that case, what will be the sampling distribution? Sampling, there won't be any distribution because only one data will be getting. We will get x bar based on 10,000, only one data, so it will be like this, no distribution. Suppose I am getting n equal to say 100. Each individual point, the n is 100. So there will be say 100 data point, 100 value. So we will have certain distribution. So we will have say certain distribution. Similarly, we can go on decreasing the number of samples. Now here in this plot we will see if we increase the sample size, so we know the standard error equal to standard deviation of population, this is population by under root n. So from this equation standard deviation of population is constant. So if we increase the number of specimen, so we will get standard deviation will be standard error. That means you are getting less and less error. That so to get the lower error percent in your calculation, in your estimation, what we should do? We should increase the number of individual, the sample size. This is the sample size. So if you see here, as I have discussed, black line, it's a only one data is there. That means it's a mean value. Now if you take say 10 data point, 10 in a sample, so each and individually, so you will get one plot is a pink color, purple color plot, then green plot, it's a 30 number of individuals, in 50. Okay. So from this plot we can see when as we go on increasing the number of specimen in a sample, the plot is becoming closer and closer towards the central value. That means error produced by the during the sampling is reducing. You can reduce the error by increasing the number of samples. So through our calculation we will discuss how to increase the confidence, how to reduce the error percent. So from here, from this plot, so for that is larger sample size means spreading is smaller. So to increase the confidence, to increase the accuracy of the data point, the result, we have to take larger sample. So this is actually contradictory. So we have to, for quicker result, n should be less. Sir, if we take 10 specimen, we will get the value quickly, we can analyze the quick result. But if we try to take the 50 individual, it will take time and cost. But with the 50 number of specimen, we will get the accurate reading, our confidence will be more. So this, there is a compromise. So we have to see, do we need the accurate result where the accuracy is important? There we can use a larger number sample, and where we want to get some idea and we need quick results, we have to use the lower number of specimen, and that we can calculate the sample number, provide if the accuracy target is given. So if you know your target, how much accuracy you need to get your data, in that case you can calculate the number of readings you have to take. Now let us try to see few numericals. The first numerical is that the set of 20 inputs has the standard error of 3.10. The value of standard deviation and variance will be approximately, what will be the requirement is that what is the standard deviation. So standard error of mean is given, we have to calculate the standard deviation and variance. So variance is nothing but square of standard deviation. So variance is standard deviation square. So from the earlier discussion, we know that standard error of mean is standard deviation of population and by under root n. So here n is given 20 and standard deviation of standard error is given 3.1. So from there we should be able to calculate the standard deviation of population, which is standard error of mean divided by under root n standard error of, it's given 3.10, n is given under root, so it's 20 individual, and the standard deviation is 13.86. Okay, and one thing what we should remember, the standard unit of standard deviation is there is a unit in that standard deviation. The unit is actually nothing but the unit of the individual data point. Like if we take the strength in centinewton per text of individual data, and this strength value here, the standard deviation unit will be centinewton per text also. So that's understanding. And then to calculate the variance, and variance is nothing but the square of standard deviation. As I have discussed, it's a square, if you take it will be 192.09. So let us do another problem, similar problem. A set of 18 inputs are there, n equal to 18 and standard error is 3.2. Value of standard, similar problem is there. Standard deviation, and this is standard error of mean. If we want to calculate the standard error of standard deviation, that I'll just discuss. Standard deviation of population, standard error of mean, and from there we can calculate the standard deviation of population, and this is the value, and here we are getting the standard deviation of population. Standard deviation of population is 13.59 and variance is 184.14. Now, if we want to calculate the standard error, this is the standard error of mean, standard deviation of, suppose we want to calculate the standard error of standard deviation, and from this, now this is one, and also in this numerical, standard deviation means standard deviation of standard error of mean. This is standard error of mean. Now, based on this given data, if we have to calculate the standard error of standard deviation, standard error of mean is given, total data point is given, we are supposed to calculate the standard error of standard deviation. So, in that case, this everything will be we have to do. Standard deviation we are calculating, standard deviation of population. So, standard error of standard deviation will be 13.57, which is the standard error of mean divided by under root 2 into 18. So, the value we can calculate, standard deviation of 13.57, 2 into 18, what will be the value? Sorry, 2.26. So, this will be 2.26. So, so standard error of mean is 3.20, but standard error of standard deviation will be 2.26. It's a factor of divided by multiplied by 2, under root 2. Okay. So, this is the basic understanding how to calculate the standard error from the population standard deviation, or how to calculate the standard population standard deviation from the standard error of mean based on a number of inputs. Now, here if we increase the number of inputs, suppose in case of 18, in place of 18, the standard error of mean is 3.2. What will be the standard error of mean for say 50 inputs? So, what will be the standard error of mean for 50 inputs? So, if 18 inputs gives 3.2 standard error, 2.26 2.172. No, just we can calculate 13.57 divided by under root under root 36, under root 36 and by 6, 13 point, that means 13.57 divided by 6, 13.57 divided by 6 is 2.26. So, 18 now the question is 18 inputs gives the standard error 3.2. 18 inputs, 18 reading gives the standard error of 3.20, standard error. What will be the standard error for when we have got 50 readings? So, that means same calculation will be there. It is standard error of mean. So, we have calculated the standard deviation. So, standard error of mean will be 13.57 0.57 divided by under root 50. The value will be 1.91. So when we increase the number of number in the sample, the standard error is reducing. That we have already discussed. So we will stop here for now. We will continue discussion on this topic in the next lecture. Till then, thank you.